Hello everyone and welcome back to an L582 modeling and control of electric machine and drives. Last time we were talking about the grid connection of synchronous generators and the behavior of this kind of generator connected to grid. The main idea is just when connected to a grid, you're held to the voltage and the frequency of the grid. And the change in the loading condition, whether it is reactive power generation or active power generation, it will not affect the terminal voltage and the frequency of the machine, because if you are connected to a strong network, the network will hold you to its values. And all the time you're using the AVR, the automatic voltage regulator, and the governor or the automatic generation control to control back the terminal voltage and frequency to the voltage and frequency of the grid and keep the machine working synchronously. Otherwise, if you does not succeed to do this, the machine will lose stability and get out of synchronism, and it don't have anything to do but to disconnect it from the grid. Okay. And all the time we use the VQ relationship and the FP relationship, the relationship between the Q and the terminal voltage, V, and the power, active power generation and frequency to just hold these operation. Okay. So basically the most important thing we talked about before last times was the FP relationship and the VQ relationship, okay, of the synchronous generator. And today we're gonna need to talk again about the FP relationship specifically, okay. So the FP relationship was just something like that. It's talking about the frequency of the generation with the generated power, the active power, directly in watts, okay guys? And it was just something like that. That means with the increase in the active power generation, the frequency go down, okay? And why we said that? Because it just happened like that. What happens in real life is just if the load increases, or it's actually the load requirements increases, okay? So if the load requirements, active power requirements increases, the generated power of your machine has to increase to meet this requirement, okay? And with the increase in the power generated of the machine, that will be just translated into increase in the counter torque inside the generator, which just acts in an opposite direction to the main torque applied by the external mechanical source to rotate your rotor, okay? So this guy, which increased, now the counter torque acts like a brake on the machine shafts, and that means the speed of the machine will drop down, okay? And the speed of the machine here equals the synchronous machine, because we're talking about a synchronous machine, yeah? That means it's totally synchronized with the frequency of the voltage generated, and that means the frequency will drop down. And that's the whole point we are talking about here, okay? That's why, like you've seen here, with the P increase, the frequency goes down. We don't like to have this happen, so we use the governor or the automatic generation control, they are the same thing, to increase, okay, the mechanical power input, P mechanical, and this increases the frequency again. But how it increases this? Actually, it increases the no load value of the frequency, which in this increases the full load frequency. What I mean by this, back to the FP relationship here. Here is 0, which means no load, yeah? So this frequency, we called it FNL, means the no load frequency, F no load, okay? So this is the frequency which this machine will be working at if there is no load at all attached to it. So it's not working to push any power to the grid. We call this state that the machine is floating. That means it's not giving power to the grid, and obviously it's not taking power, because taking an electric power from the grid means it's a motor, not a generator, and we do not play with this, okay? So that is the frequency which is the machine working at, which is not giving any power to the grid. We call it the no load frequency. But what really happens is if you pushing power as much as the full load, FL means full load, okay? So that is the full load power, the rated power that the machine can deliver to the grid, okay? This is corresponding to this value of the frequency, which is frequency f load followed. Okay, so what happens with the governor action, it really does, is for some reason if you have to do this, so if the power increases, so what's happening here, if you are working at the no load, you're working at this kind of frequency. Okay, if your generation increased to the full load, you're now working at the f full load at this operating point. Yes, why do you need to increase this frequency? Okay, if you just, this frequency is not a good, actually it's not the typical case, because like we said before, we're designing the machine to work out all the time at the full load power, and this is corresponding to the full load frequency, and actually this is designed to be the system frequency. Here in North America it's 60 hertz. Okay, but if for any reason we wanna change the frequency that the machine working on, now we will using the governor action or the automatic generation control to actually change the frequency. Okay, and this happens actually by just using another curve like this. So if the governor increases the active power, the mechanical power input like this, so this is the governor action increasing the mechanical power input. So you're now working at a different FP relationship, the blue one, this one. Okay, so at the same power here, now we're working at this point. Okay, taking this point back here will give you the same frequency we're working on before. So it's still pushing the same power, the full load power, but at a higher frequency. And this is all the action of your governor here. What the governor did actually is he increased you this value now. That is the F no load 2. That was F no load 1. So the governor, by increasing the mechanical power input, is basically increased the no load frequency too. So if you're now working at this increased FP relationship, call it FP relationship 2, that means if you're now working at this and the power has been just stopped, so you don't have any load and you're back to no load, now the frequency will be this high value. Now the no load frequency 2, F no load 2, because you're already working at a higher FP relationship by increasing the input mechanical power. And this is the action of your governor or automatic generation control. Okay, guys? So what actually this guy is doing, the governor is doing, is like you have an F here, and that is P generation. So you will have different FP relationship, depends on your governor action. Okay, with the increase of the mechanical power input by the governor action, you will be working at any of those. So from relationship FP relationship 1 to 2 to 3, they are all curves. By changing this value, this is F no load 1, this is F no load 2, this is F no load 3. So the governor action is actually increasing or decreasing the no load frequency, and by doing this, it's actually changing the FP curve you're working at. So it depends on whatever load you want to generate now. So if it is the P generated for a certain load, okay, it depends on whatever FP relationship you're working at, it will determine the frequency you're working at right now, the actual frequency you are working at, what we call the system frequency most of the time. Okay, guys, so for you to know that the governor action is to change the no load frequency F no load. Okay, and this means working at different FP curve. Actually it's FP line, but you got the idea. Okay, guys, good. So how to actually quantify this FP relationship, because we'll be dealing with this all the time. We did this before, but it's worth mentioning again. So if it's FP generated, okay, again, that is your line here. So this line, like any kind of a line, has a slope. Okay, we call it SP, just to know it. Okay, this value here is the F no load. Okay, and it depends at here. So here at the P full load, so this going here to F full load. Okay, and obviously the zero power, it is the no load power, because basically P no load is 0. Okay, so if you want to do this, how to quantify this slope? Like any slope of any line, it is delta P over delta F. Okay, so delta P is the P full load minus P no load, and delta F is F no load minus F full load, because F no load is higher, and anyways we need just the magnitude of this slip, so it doesn't matter if it is positive or negative or now. Okay, so the P no load is equally 0, like that. Okay, so that is your slope of this FP relationship, the P full load divided by F no load minus F full load. That's a good relationship, keep it in mind. And doing this, we can find this. That means that P generated at any time is the multiplication of the slope, which is constant for all the line, multiplied by F no load minus not just F full load, but F system. Why? Because now you can use just this slip to find any power at any point. So it's not just dedicated for the full load, but you can find any power you're just working at, depending on its frequency. Okay, guys? So if you wanna, for example, to find this P now, P generated, okay? You need to find which frequency it's working at. So call that F system, okay? Because it's using the same FP relationship, so it's the same slope here, so you can use this slope with this relationship here to find it, okay? So you just use the no load frequency, which is just constant here for all the relationship, and you need to find at which system frequency you're working at, and it is the same slope, and you can find the amount of power, okay? That's that. So that's in watts, obviously. We're talking about active power here. Okay, guys? A very nice actually application on this and using the FP relationship and all that stuff is a nice application. We use it here. It's how to determine the load sharing of two similar sized generators. So remember when we talked about before is if you have here an isolated load like that, so that is load, Z load, the impedance of the load, okay? I'll just call it that is load for now, because I'm not gonna use the equivalent circuit diagram directly, yeah? And you just, this load is big enough, so we need to use multiple generators to feed it. Here, specifically, we're using 2 generators, and those 2 generators are similar size. So they are the same size. That means they have the same rating, the same rated power, rated capacity those they can deliver. But rather than just having one big generator to feed this big load, we will use 2 generators in parallel like this, okay? So that is synchronous generator 1, and that is synchronous generator 2, okay? So the power needs some power, the load needs some power, P load, and this will be shared by the 2 generators. Generator 1 will have P generated 1, and generator 2 will have P generated 2, okay? So obviously P load will be shared by the 2 generators, P generated 1 plus P generated 2, okay? And that's what I mean by load sharing of 2 similar sized generators, okay? So if you have the load to equal 1,000 megawatt or something, that means the 2 generators will be sharing the load equally. Each one of them will be having 500 megawatt. Now it's different. Why? Because each generator has a different FP relationship. Okay, let's see this, how this will be happening. Okay, so P generated 1 or P generator 1 will equal like the same one as SP1, the slope of his own FP relationship, multiplied by F no load 1, because he has his own no load frequency, minus F system. And P generator 2 will be SP2 multiplied by F no load 2 minus F system. So each of the 2 generators has its own slope, of the FP relationship because they have different FP relationships, and they have different no load frequency because the no load frequency is just controlled. So if no load 1 and if no load 2, they are just managed by the governor. Okay, so it is something you can control using the governor, and because there are two different generators, each one has its own governor, so it's something controllable. So if no load 1 may be different from if no load 2 because that's something is under your control. Okay, the whole point is if system 1 or if system is the same, you don't have different if system. Why? Because like we said last lecture, if you are just connecting two generators in parallel like this, they have to work at the same frequency. So the system frequency, the actual frequency they are working at this load, it has to be equal. Otherwise you will start having a circulating current moving between the generator, and this can damage both of them, and we don't do this. Okay, that's why you can have different no load frequencies, but the actual frequency, the system frequency, has to be the same. Okay guys? Okay. So to determine actually the load sharing between those two similar sized generators, we use a very famous diagram. We call it the house diagram. Why are we calling it a house diagram? We'll be just seeing it now. Okay, so the house diagram is basically plotting the FP curves of the two similar sized generators together. Okay, how this? So you just have it like that. So I will be having a relationship of them, FP relationship like this. This is the frequency, and this is P generator 1, and this is P generator 2. So it's not a positive and a negative sides of the axis. Both of them are positive, but it's just we are plotting them together on the same one. Okay, so the right hand side part here will be the FP relationship of generator 1, and the left hand side will be the FP relationship of generator 2. Why are we using this? Because it will be just a sketch tool you can use actually to find the load sharing and the system frequency of those two generators together. Okay, so having something like that, so the FP relationships will be just like that. So here you're plotting the FP relationship of the first one, sorry. Okay, it will be like that. Okay, so that is the no load frequency of no load 1. Okay, and here the FP relationship of the other one, that is the F no load 2, and that's it. Okay, and how to find the load sharing, how to find for some power the load power, how they are sharing it. So you'll find the same, the power of the load, and you just plot it up to scale on this graph like that. Okay, so the power will be acting like this. So this green line here represents the load power. Okay, once you're able to plot it, you can just move it up and down until it hits on its two ends with the two graphs like this. Okay, and this will give you all the information you want. Go down from here, and this will give you P generator 1, how much power come from the first generator, and go from here down, that will give you P generator 2, how much power is coming from the second generator. So this how much the second generator will share, and this how much the first generator will share. Okay, and this point here is the F system, the system frequency, the actual frequency the two generators will be working at the time. Okay guys, so that's it. What's in your hand to do? What in your hand to do is controlling using the governor, and the governor will just change the FP relationship of each of the two generators up and down. It's up to you. And what will happen if you just move one of them up or down? Okay, so let me have an example here just to show you what's happening. So I'm gonna plot this again down here. That is P generator 1, P generator 2, and that is the frequency. Okay, what happens if I just use my governor of the generator 1 to just reduce the no load frequency? So that means reducing the mechanical power input to generator 1. What will happen is, so for 2 it will just remain the same like this. I'm trying to make it as much as it, if no load 2. Okay, by using the governor of generator 1 and reducing it to be just touching it at the same no load frequency like this. Okay, this using the governor of generator 1, okay, to reduce it like that. So now if no load 1 is the same as if no load 2, okay, what will happen is the same amount of P load at the first you're trying to share like that will be now like this. Okay, that is P load. And from here now the sharing now different. See, now the P generator 1 now, and that is P generator 2. So now they are sharing the load almost equally. Almost, they're not equal because they have different slope of the curves of the FP relationships. Okay, and now also you have a change in the system frequency. So the system frequency is not the same as the first one. Okay guys, I'm not calling out 1 and 2 because it will confuse. The two generators are the same, but I'm talking about case 1 and case 2, okay? That's what I'm saying. So you can control both of them. You can control the governor of the first one and the governor of the second one, or you can control them together. It's now up to you, okay? So keep that in mind. Changing, or let me call it controlling, okay, the F no load of one generator alone changes the power sharing, okay, and the system frequency, while changing the no load frequency, F no load, of the two generators together at the same value changes the system frequency F system, leaving the load sharing unchanged. What I mean by that, it'll be a lot of work to just keep redrawing all of that, so I will take you to, again, Dr. Knight online materials. It's very useful here to do. So that's an interactive house diagram, okay? And by the way, you now know why we call it house diagram, because it looks like a house by just plotting the two generators FP relationships on the same relation. It will just have this triangular shape of the house, okay? So here you have the patterns to increase P, decrease P, increase F system, decrease F system, and to increase and decrease H no load frequency of them all, okay? So that was the first case. So the black line in the middle, it's just the load power that you need to share. And right now, both of them have the same no load frequency by the action of its governor. What happens if I need to increase the load? So if the increase goes higher, so you just increase the load by increasing P. See what's happening? So the increasing P, the load has just gone up. The sharing of each of the generator will increase, obviously, because the load has just changed. And it's just going down. That means the system frequency will go down, because the system frequency in the intersection between the load power and the vertical frequency line. Yes, guys? If this decreases and goes up, if the load decreases, that will go up like this. That means the sharing of the generator will decrease. Each one will just have less power, but now the system frequency goes up. Okay, guys? If you're talking about this and you want to hold the frequency at 60 hertz, that will be a constraint to keep in mind. But for now, we don't play with this. But now you see what's happening if you need to increase or reduce the power out. That means the load increased or decreased. If the load increased like this, the sharing from each generator will increase, but the system frequency will go down, will decrease. If the load decreases, the sharing of each generator will be decreased, and the system frequency will go up. Obviously, each generator of them will have a capacity. So, if you're increasing the power, sometime one of the generators will hit its maximum. It cannot go beyond this value, and that means you cannot hit this. Otherwise, you will burn your generator winding. Okay. What's happening if you need from this one to control the system frequency? Like here is the system frequency, like it's saying here is 60 hertz. What if I wanted to increase or decrease the system frequency without playing with the load sharing? So the leads stay the same. So if you increase or reduce the system frequency, you want to increase system frequency. What's seen here is use the governor to increase the two no load frequencies. So you use the two governors of the two generators at the same time and increase or decrease them as you want, but the same magnitude of increase and decrease of the same of the two generators. Now you're controlling the system frequency up and down without playing with the load sharing. So each of the two generators still have the same power to have, but at different frequency by controlling the two governors together at the same time by the same amount. Does that make sense? Okay. But what happens if I increase the no load frequency of one alone? Seen here? With increasing it, you are increasing its own share, and this reduces the other share, okay? And also it's making the system frequency higher, okay? Seeing that? Going back. So if I increase F no load 1, with the increasing of no load 1, you're increasing its own share of power and increasing the system frequency while reducing the share of power of the other one. Maybe you hit sometime is just the P of the generator one is just feeding the whole load on its own and nothing coming from the other one. If you can do it, if you won't do it, you can do it, but it doesn't make sense, yeah? And this increases the system frequency also. Okay, guys? The same thing if you do with the other generator. Of the generator 2 now of increasing its no load frequency by using the governor, its own governor, without touching the governor of the other generator, you increase its own share of power and increasing the system frequency. Okay, guys? Make sense? So yeah, you can do this interactive one on doctrinate and raw material. Play with it. It will just give you much understanding of the house diagram and how it works. Okay. Actually, a numerical example will help here so much. Okay. So let me grab you a numerical example. Okay, I think this one. So let's try to solve this one together. I will help solidify this concept a lot. So we can solve numerically. We don't need to do actually the graph, okay? Because they're basically equations that you can go on together, okay? So let's analyze the data here. So it's saying that we have two generators operate in parallel to supply load, which is our case. Generator 1 has 4 poles. So generator 1 number of poles is 4. And SP1 is 5 megawatts per hertz. That's the slope of its own FP relationship, 5 megawatts per hertz. Generator 2 has 16 poles, that's number of poles. And its own slope of the FP relationship, SP2, is 4 megawatts per hertz, okay? That's the case shown in similar size generators page. So if we just refer back to Dr. 9 online material, you can find the same example he used. If the load is 1.4 megawatts, that is the load power you have to supply. If no load 1 is 60.1 hertz, and if no load 2 is 60.05 hertz, that is the setting of each governor of each generator. Okay. Calculate the system frequency, F system, the rotational speed of each generator in S1 and in S2, and the power supplied by each generator. The load sharing, how much power will be supplied from each generator. Okay, guys? So it's very useful to summarize for yourself those ones. So for generator 1, number of poles P equals 4, and the slope of the on curve is 5 megawatts per hertz. Okay. For generator 2, the number of poles P equals 16, and the SP2 all equal 4 megawatt per hertz. Okay. For number 1, or for number 1, he wants you to find him, or still given that P load equals 1.4 megawatt, the F no load 1 equals 60.1 hertz, and the F no load 2 equals 60.05 hertz. And he wants you to find him the system frequency. Okay. So actually you can try to plot this as a visualization here, okay? That is P generator, I call it 2, and that is P generator 1. Here is the frequency, okay? So according to those relationship, for P generator 1 on the left, here it's on F no load 1, which equals 60.1 hertz, okay? And the slope of this curve is P1 equals here 5 megawatts per hertz. Given attention with the units, okay? And here's F no load 2 equals 60.05 hertz. It's a little bit down, and the slope of this curve is P2 is 4 megawatt per hertz. Okay, what you need to do is just having the power he wants you to find, 1.4 megawatts, and just plot it on the same thing, okay? And find the sharing. Here P generator 2, P generator 1, and here is the F system, the system frequency they are working at together. Okay guys, how to do this? It should be easy. We know that the load power that's required to be fed here will be coming from both the generators, P generator 1 plus P generator 2, okay? And you use the equation for each one of them. P generator 1 is SP1 multiplied by F no load 1 minus F system, this plus P generator 2 SP2 multiplied by F no load 2 minus F system. Okay guys? And write down what you have from those. P load equals 1.4 megawatts. So I will not multiply by 10 to the power 6, because I will just hold all the powers here to be megawatt, and that's good. Okay. The slope of the first one is 5 megawatts per hertz, so it's 5 megawatts, so it's 5. Multiplied by the F no load frequency of 1, which is 60.1, minus F system, it is required, plus SP2 is 4, multiplied by its own no load frequency, 60.05, minus the system frequency, which is required. So everything's known here except for the system frequency, so you can solve for this easily to find the system frequency now, which will be 59.922 hertz. Okay, so that is the system or the frequency where both of the two generators will be working at this time. Okay guys, so that is the first one, or this is number 8. Number B, he wants you to find him the rotational speed of each generator, NS1 and NS2. Okay, so the synchronous generator of the synchronous speed of the first generator, NS1, equals 120 F over P. F means the frequency that the generator works on at now, which is the system frequency. Please don't make a mistake here. So the generator does not work at the no load frequency unless it's working at no load. But the generator is not working at no load, it's working at feeding some load, so it's working at the system frequency. So the two generators are actually working at this point, at this system frequency, because each one of them is supplying an amount of power. Okay guys, So don't be confused. When trying to find the speed of the generator, it's 120 F system over P of the first generator's mean number of poles. So 120 of the F system, 59.922, divided by number of poles for the first generator, which is 4. So that's giving you 1797.67 RPMs. Okay, the same like for the other generator, and S2 equals 120 F system, the same frequency they're working at together, divided by P2, which is 120 F system 59.922 divided by number of poles of the second generator, which is 16. That give you 449.42 RPMs. Okay, guys? I'm giving you a nice hint here, okay? For the first generator, it has 4 poles. For the second generator, it has 16 poles. So the second generator has much higher number of poles. Seen here? That requires that the first generator working at a very high speed to achieve the same frequency, the system frequency, while the second generator can work at a much lower speed. Okay, the first one is almost 1800 RPMs, while the second one is just less than 500 RPMs. Why? Because you have much higher number of poles for the second generator. So keep that in mind. And that's why, if you remember when we talked about the difference between the cylindrical and the salient pole rotors of this generator. Okay, guys? And we just said that for the salient pole rotor, that we use it with the low speed applications because it's not as mechanical rigid as the cylindrical one. So with using that, most of the time with the salient pole rotors of the synchronous generator, you found it has much higher number of poles. Why? Because it typically works at lower speeds. So that's why you needed high number of poles to achieve the same frequency. While you work on the cylindrical rotors and you already work with a very high speeds, so the speed is just compensating for this, and you don't need as much number of poles. Why? Because actually more number of poles means more cost, more manufacturing complications and all that stuff. Okay, guys? So I will just hint coming from the numbers, and that's why I'm telling you all the time, look at the numbers. It's engineering principles. So because one of them, so you have a big difference in the number of poles, it has to be obvious that the generator with less number of poles will have much higher speed than the other one. So if your calculations didn't have this or doesn't land you with these results, that means you're making a mistake. So stop with the numbers. It's something so important to look at the numbers while you're trying to solve. Okay, guys? Okay. After this, he wants you to find him the load sharing. So P generator 1 and P generator 2. How much power B supplies from each generator. Okay? So it should be easy because we already found it before in the equation. So P generator 1 equals SP1 multiplied by F system, which now we calculated, minus F, it's F no load 1 minus F system. Okay, so the slope of the first one is 5 megawatts per hertz multiplied by F no load 1, which is 60.1, minus the F system we calculated, it's 59.922, and this gives you 888.89. Don't forget, okay, you have to look at the units, and here will land you with kilowatts. Okay, so if you just multiply this, it will give you something like 0.889, something like that, megawatts. Okay, so I just multiply by 1000 and it's 888.89 kilowatts. Okay, guys? Good. The same like if you calculating for P generator 2 as SP2 multiplied by F no load 2 minus F system. And this give you the first one is the second one is the slopes 4 megawatts per hertz. Its on no load frequency 60.05 minus the system frequency 59.922, and this equals 511.11 kilowatts. Okay, guys? by the way, it's obvious that you have to just, if you added those two together, it gives you the 1.4 megawatts, which is the load power. Otherwise, again, you're doing a mistake. And actually, you can do it like that. You can find P generator 1 like this and say that P generator 2 equals P load minus P generator 1, and you don't need to recalculate it. But I suggest you recalculate it just to make sure. Okay, guys? Okay. That was number A, or the first case. The second case, if the power is constant at 1.4 megawatts, so you still have to feed 1.4 megawatts. But now he's playing with the other one, so sorry, the no load frequency of the first one is 60.1 hertz. It doesn't change it. What value of N no load 2, the no load speed of the second generator, is required to adjust system frequency to 60 hertz? That's the whole point. We just calculated for the first one and found that the system frequency is 59.922 hertz, which is different from 60 hertz, the system frequency we are working at here in North America. So that's something wrong. We don't like to do this, okay? So he's asking you what to do with the second generator, how to adjust it with the governor to restore the system frequency at 60 hertz. Okay? And that's a good one. Let's investigate the same thing here. Okay? So for number 2, sorry, he wants your system frequency to be 60 hertz. Okay? That's given now. I want my system frequency to be 60 hertz. The no load frequency of generator 1 still 60.1 hertz. We don't play with it. And the load power we want to feed still 1.4 megawatts. You need to find the no load speed of the second generator, which is totally related to the frequency at no load. Okay. So let's figure out what's in our hand now. First of all, I know the no load frequency and the system frequency was the first generator. So you can find how much power be generated from this kind of a generator. P generator 1 will equals SP1 multiplied by F no load 1 minus F system. Yes? SP1 is 5. It's not changing the slopes because just something for each generator we don't play with, yeah? So the slope is 5. No load frequency of it 60.1 still, but the system frequency now is 60 because we want it to be like that. If you multiply that, it will give you 500 kilowatts, okay? Which is 0.5 megawatts. Okay, guys? So I know how much power generated from the first one. And this can be used directly to find how much power will be supplied from the second one. Basically, it equals P load minus P generator 1. So it's 1.4 megawatts multiplied by 10 to the power 6, not to confuse you, minus P generator 1, which is 500 kilos, 510 to the power 3. And this will give you 900 kilowatts, okay? So that's the load sharing now. 500 kilowatts from the first one, 900 kilowatts from the second one, okay? And we can use this to find the no load frequency of generator 2. Why? Because you know that P generator 2 equals the slope of it, SP2, multiplied by F no load 2 minus F system. You know the P generator now, 900 to the power 10 to the power 3. SP2 equals 4 megawatts per hertz. That means 410 to the power 6. Multiplied by F no load 2, which is not known here, minus the system frequency was 60 hertz now. Solve for this, and this give you F no load 2 to be 60.225 hertz. Okay, guys? That is the no load frequency of generator 2. It wasn't required. What he wants to find the no load of it, the no load speed, and no load 2, which is obvious. 120 F no load 2, because I want you to find him the no load speed, not the actual speed. Okay, so it's 120 F no load 2 over the number of poles of it. Okay, guys, that will have you equals 120. The frequency you have just calculated 60.225 over the number of poles, which is 16, that will give you 451.688 RPMs. That is the speed required. That is the no load speed required for here. So that's the whole point. Is at the first case it was like that. The other load sharing and the system frequency was less than 60 Hz. So I was asking you if I can control the governor of generator 2 to restore my system frequency back to 60 Hz. What I need to do. So he has what he just did. So the no load frequency of the generator 2 from here was 60.05 Hz. Okay, so that means with our calculations we told him that we need to use the governor to increase the no load frequency to 60.225 rather than to be 60.05 before. This will adjust the system frequency to 60 Hz and will slightly change the load sharing between the two generators. Okay, guys? That was a suggestion from an engineer. He said, or that was the problem in the first part, that the load sharing of the two generators resulted in the system frequency is not at 60 Hz. So he will ask you if this is a good option to use the governor of the second generator to increase the mechanical power of it a bit. Okay, that could be fine if you have the capacity of the two generators, which is not given here, but it may be given. So if you do something like that, and it said, but make sure that the capacity of generator 2 cannot exceed 800 kilowatts. So if you just use this, your calculation found out that generator 2 at this case has to generate 900 kilowatts. But if the capacity is 800 kilowatts, the rated power of it 800, that means you are exceeding it. So it's not a viable solution. So we need to find another one. Maybe you will leave generator 2 as its own and increase the mechanical power of generator 1. Play with F no load 1 rather than F no load 2. Okay, guys? So that's the whole point. It's different engineering solutions. You are just working with this. You're looking at the two different generators with two different settings and see how actually to change these control settings to meet the load requirements at the system frequency you want without exceeding the limits, the power limits of each generator. Okay, so you may have the same problems like that, but he will give you some what we call power limits for each generator. So you cannot exceed the power limit of each one. You are calculating and finding P generator 1, P generator 2. Those values cannot exceed the limits that's required for this generator. Okay, guys? Okay. So today we're talking about the house diagram. That means how to share a power between two similar sized generators and how to use this graphical tool, which is the house diagram, to find out the sharing of power and how to calculate or how to find the frequency they are both will be working at to be sharing at this level of power sharing. Okay. Have time to review this and try to solve examples over it. You'll find some solve these examples in Dr. 9 online materials, and you'll also have an assignment about this, and you can find more questions on your recommended text box beyond. Okay. Thank you so much for joining me today, and I hope to see you next time.